Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how to calculate the amount of refrigerant you need in order to freeze a certain amount of water into ice cubes. So let's get into this. Okay, so for this problem we're going to start off by reading the problem. It says that an ice cube tray is filled with enough water at 22 degrees Celsius to make 18 ice cubes weighing 30 grams each. The tray is placed in a freezer that uses CF2Cl2 as a refrigerant. As cold liquid CF2Cl2 runs through the refrigerator coils, it absorbs heat from the freezer and vaporizes. So the CF2Cl2 is going to vaporize because it's absorbing heat, gets above the boiling temperature, and therefore vaporizes. The heat of vaporization of CF2Cl2 is 158 joules per gram. What mass of the CF2Cl2 must be vaporized to convert all the water in the ice cube tray into cubes at negative 5.0 degrees Celsius? And they give us some information. Oops, I'm going the wrong way. So we have the specific heat of water, 4.818 joules per gram degrees Celsius. Specific heat of ice at 2.03 joules per gram degrees Celsius. And we have the heat of fusion, which means melting. Fusion means melting. So we have the heat of melting of water at 6.02 kilojoules per mole. Also, I have a heating curve here that kind of represents what's going on in the problem. So we're starting with water at 22 degrees Celsius, and we're going to cool down the water. So I fill up the ice tray. It's enough water to make 18 ice cubes, and there's 30 grams each. So I take my tray, I open up the fridge, I put the tray in the freezer, shut the door, and now the freezer is going to cool down the water. So it's going to cool it down until it gets to ice at negative 5 degrees Celsius. So I'm starting here and I'm ending here. So I start with liquid water at 22 degrees and I end with solid water, ice, at negative 5.0 degrees. So during this process, we're losing energy. The water is losing energy. So it's an exothermic process. So if the water is losing energy, that energy has to go somewhere, and it's going to the CF2Cl2 refrigerant. So the refrigerant is absorbing that heat from the water, and the water is losing heat. So here we're assuming that there is no energy lost. All the energy that was in the water in the ice cube tray has now been absorbed by the CF2Cl2 to vaporize it. So that's the backstart. That's the setup. So what does this mean? It means that the amount of heat absorbed, Q is the amount of heat lost or absorbed. So Q of A is going to be equal to, but opposite of the amount of Q or heat that was lost or released. So this is equal. So this is the law of thermodynamics, that no heat is lost during the process. So here we have the amount of heat absorbed by the CF2Cl2 is going to be equal to the amount of heat lost by the water, the amount of heat released by the water. So these two are equal. Now, during the process, we have to remember that when we're figuring out the thermodynamics of the loss of heat by the water, notice that we're dealing with water as a liquid here. It loses its temperature, but then here we're talking about the freezing of the water here. So we're going to have to calculate the amount of heat lost here at this step, right, during the process where energy is lost from the water. But then we have to consider the amount of energy lost during the freezing process. And then here, once all of the water is frozen, we now have to calculate the amount of heat that is lost due to the the temperature change of the ice. So we have three parts: the temperature change due to the water, the freezing of the water, and the temperature change of the ice once it's frozen. So that's three parts that we have to take in consideration. Three parts or steps at which water is losing energy. So for these parts where there's a temperature change, you're going to use the Q equals MCAT equation. So the Q of water in this part is going to be equal to the mass of the water times the specific heat of the water times the change in temperature of the water, which is final minus initial. Now for this part, with the freezing part, that's going to be a different equation. So here, the Q, or we'll just say the heat of fusion, delta H of fusion, the heat of fusion is going to be equal to, or I should say Q, let's say Q. So the Q of freezing, QF, is going to be equal to the heat of fusion that we're given here. Notice that the heat of fusion has the units kilojoules per mole. So we are only interested in the energy unit, kilojoules or joules. So if the heat of fusion is in the units of kilojoules per mole, we're going to have to get rid of moles. And since moles is on the bottom, we're going to have to multiply the moles of water we're freezing. So here we're going to have to multiply that by N of the water, the amount of water we're freezing. So the number of moles of freezing multiplied by the heat of fusion is going to give us the amount of heat that was released during the freezing process. That's why I have QF. So that's stage two. And then the final stage is the temperature change of the ice once it's frozen, when it's made. So the Q of ice is going to be equal to, again, since we have a temperature change here, we're going to use Q equals MCAT. Anytime you have a temperature change, you would use Q equals MCAT to find the amount of heat that is absorbed or lost in the process. So here we're going to have the mass of ice multiplied by the specific heat of ice multiplied by the temperature change of ice. And again, the temperature change is final minus initial temperature. So all of these three together gives us the total amount of heat lost by the water while it's cooling in the freezer. So this is QR, the amount of heat released. Well, where did all that water go? I'm sorry, where did all that heat go? It went to the CF2Cl2. It went to this in order to heat it up and vaporize it. So that's going to be the QA. So QA, which is going to be the Q of CF2Cl2, well, how much heat was absorbed by the CF2Cl2? Well, they give us the heat of vaporization, and notice it's in joules per gram. So This is going to be the heat of vaporization they give us. Now notice it's in joules, so that's an energy unit. That's what we want, but it's joules per gram, so we're going to have to get rid of grams. And since grams is on the bottom, that means we're going to have to multiply by the mass in grams. So this is going to have to be multiplied by the mass of this CF2Cl2. So this is equal to the heat absorbed. And so all we need to do is take all of this, put it on one side, and take this and put it on the other side. Now, there's another form that you can use, and this is the form that I like to use. If we bring the negative QR on one side, then we would just add QR, add QR to both sides, and then what we get is we get this side is going to be canceled out, that's going to be equal to 0. And so we're going to get 0 is now equal to these two added together. Q absorbed plus Q released. So you could either use this form or you could use this form. It really doesn't matter which form you use. The only thing you got to remember is that in this side here, you don't have to worry about having the negative there. You do have to worry about negatives here. So make sure that when you do the final minus initial, that it's a final temperature minus initial temperature. If you get a negative, that's okay. If you get a negative, that's okay here. It will work itself out. The negatives will cancel out. At some point, it'll work itself out. So you could use this end, but you need to have that negative there because that negative will help to cancel out negatives here and here if you've got them, right? If you use this point, you don't have a negative, but again, if you do get negatives for the change in temperature, that will work itself out. So you just got to be careful about your data and when you plug and solve the equation. Okay, so I'm going to go ahead and use this form here. So I'm going to go ahead and set it up. So here, let me erase this, give myself some room. Okay, so I'm going to use 0 is equal to the Q absorbed plus the Q released. So basically everything goes to one side. So all of this I'm going to go to one side and then 0 on the other. So this means that 0 is going to be equal to all of this. So Q of the water when we cool it down plus Q of freezing when we freeze the water plus the Q of the ice when we lower the temperature of the ice plus the Q of the CF2Cl2 when it absorbs that energy. CF2Cl2. So 0 is equal to all this. So all I need to do is substitute all of this for each one of those. So let's go ahead and do that. So I have Q, or 0, I should say, 0 is equal to QW. Well, that's this. So that's going to be the mass of the water times the specific heat of water times the change in temperature of the water plus QF, which is this. So I'm going to add to that delta H of fusion, the heat of fusion of water times the number of moles of the water. And then next I have Q of ice, which is this part here. So again, it's MCAT, but this time it's the mass of the ice times the specific heat of the ice times the change in temperature of the ice. And finally, I have to add this. I don't have enough space, so I'm going to go ahead and erase this now. So plus this here, so it's going to be the heat of vaporization of the CF2Cl2 times the mass. And that's going to be CF2Cl2. Okay. So now I have the equation set up. Now all I need to do is plug and chug. Now, there's one thing I need to keep in mind here. So this is in joules, and this is in kilojoules. This is in joules as well. So everything's in joules except for this. So this is in kilojoules. So I need to make sure that I convert that to joules. Since everything else is in joules, I can convert that to joules. So here, that's the heat of fusion. That's this here. So I'm going to have to multiply that by 1,000 because notice kilojoules is on the top. So if I multiply that by my conversion factor, I know 1 kilojoule is equal to 1,000 joules. So I would have to multiply by 1,000 to get to joules. Kilojoules cancels out. So I'm going to need to do that. Okay, so let's put in the values here. So I'm going to need to make more space. So 0 is equal to the mass of the water. Well, the mass of the water is, they say I have enough water to make 18 ice cubes at 30 grams each. So I need to multiply 30 times 18 to get the total mass of the water. And that's going to be 540 grams. So we'll put in 540 grams. Let's make sure we have the units, grams, multiplied by the specific heat of water, which is right here, specific heat of water, 4.18. So 4.18 joules per gram per degree Celsius, multiplied by the temperature change. So remember, the temperature change is final temperature minus the initial temperature. The final temperature here is going to be 0. So we're going to cool it down, liquid water, from 22 degrees to 0 degrees Celsius. So the final temperature is 0. The initial temperature is 22. So final minus initial is going to be 0 minus 22 degrees. That gives us a change in temperature of negative 22 degrees Celsius. So we're going to have to put in that 0. So final minus initial, 0 degrees Celsius minus 22 degrees Celsius. Okay, we got this part. Now it's this part here. So we're going to add, it's the heat of fusion for water, which is what we're given here, 6.02 kilojoules per mole. But we're going to need to multiply that by 1,000 to get to joules. So let's go ahead and put that. So it's going to be 6.02. Let's see, 6.02 times 1,000, and that's going to be joules per mole. And then we're going to multiply that by the number of moles. Now, to get the number of moles, we need to take the total mass of water and divide that by the molar mass of water. So we said the total mass of water was 540 grams. So we're going to have to use the molar mass of water. Molar mass of water is about 18.016. So that's 18.016 grams of water on the bottom and 1 mole of water on top. So here we have water, water, water. So grams cancels out. We got moles. And when we calculate that, we get 29.97 moles of water. So now we can put that here. So what I'm going to do is I'm going to go ahead and do this calculation. So this is going to be, let's see, 6020 joules per mole times 29.97 moles. Okay, so we have these two. Now we have to add the next two. So we have this, we have this, now we have this and this. So the mass of the ice, so next we're going to add the mass of the ice. The mass of the ice and the mass of the water is exactly the same because freezing and cooling, freezing, any phase change is not going to change the mass. So that's still the same. So freezing the water doesn't change the mass. So it's 540 grams. Let me write that better. So 540 grams of ice multiplied by the specific heat of ice, which we have here. Specific heat of ice is 2.03. So 2.03 joules per gram degrees Celsius. Multiplied by its temperature change. Now the temperature change of the ice is right here. So initial temperature is 0, final temperature is -5. So remember, it's final minus the initial. So the final temperature, -5 minus 0. So here it's going to be -5.0 degrees Celsius minus 0 degrees Celsius. So now we have the ice. And then finally, we're going to add the delta H of vaporization. So the vaporization of the CF2Cl2. So we're going to add to that the heat of vaporization of CF2Cl2 is 158 joules per gram. So 158 joules per gram multiplied by the mass of the CF2Cl2, but that's what we're looking for. We don't know the mass, so that's going to be our unknown, the mass of CF2Cl2. Okay, so now we have everything set up. So all we need to do now is solve this equation. So let me go ahead and erase the board, so give myself some room, and we'll continue. Okay, so let's go ahead and start to simplify and calculate things out. So I'm going to start with this part here. So you'll notice that grams cancels out, the degrees Celsius cancels out, leaving me with joules. So if I multiply this together, I'm going to get 0 is equal to negative, because this is a negative. So 0 minus 22 is negative 22. So it's going to be negative 49,658.4 joules, since we have joules left. So that's that part. If we calculate this, we get 180,000. Hold on a second. So we have moles here and moles here. That's going to cancel out, leaving joules. So this is going to give us 180,419.4 joules. Okay. And next, we have this part here. So we'll calculate that. And oh, one of the things I forgot to mention, now here we have the heat of fusion. So one of the things I forgot to mention, and I apologize for that, is heat of fusion is melting. We're not melting something. So in order to melt something, you have to put heat into it. So it's positive. It's gaining energy, so you're putting heat into it. If you're going in the opposite direction, that would be the heat of freezing, right? But here's the thing. The numerical value of the heat of freezing and the heat of melting is exactly the same, except they differ in sign. So if you are melting something, you would use the heat of fusion with a positive sign. But if you're freezing something, then you're going to use the same heat of fusion, but now you're going to make it negative to make it the heat of freezing. So this should be a negative sign over here. So I forgot to put the negative there. So since that's negative, then this would be negative as well. Sorry about that. Hopefully someone caught it in the audience. Okay, so next we have this part here. So again, notice the temperature -5 degrees -0. So this is going to end up being a negative value. This makes sense because remember, we are cooling down the water. So as we're cooling down the water, we're losing energy. We're taking energy away. So here, all of our values should be negative, right? So that's why this should be negative, right? So whenever you are doing a calculation, make sure that it fits and makes sense with the situation. So one of the ways I caught myself is I noticed that that was positive, and I'm like, wait a minute, why is that positive? We're freezing the water. The water should be losing energy, not gaining energy. So that's how I caught my mistake. So here, negative, here should be negative as well. So I'm going to, again, cancel out the units. So grams cancels out, the degrees Celsius cancels out, leaving me with joules. So when I calculate this, I'll get joules, and I get -5481. So -5481 joules of energy. And finally, I have this here. So we're just going to add that at the end. So it's plus 158 joules per gram multiplied by the mass of CF2Cl2. So now it's much more simplified. So I'm going to go ahead and erase this now, give myself more space. So now all I have to do is add these three numbers together. So that's going to be 0 is equal to, when I add those two numbers, I get -235. Oops. -235,558 0.8 joules plus this part here. So 158 joules per gram times the mass of CF2Cl2. Now I'm going to bring this over to the 0 side. So I want to kind of separate this so I can solve for the mass. So I'm going to add 235,558.8 joules to both sides, plus 235,558.8 joules. So that's going to give me 235,558.8 joules is equal to 158 joules per gram multiplied by the mass of CF2Cl2. Now all I need to do is divide both sides by 158 and I get my mass. So divide this by 158 joules per gram. That cancels out. Divide this by 158 joules per gram. Notice I have joules here and joules here, so that's going to cancel out, leaving me with grams. So when I divide this, I'll get my answer, and it is 1490.8 grams is equal to the mass of the CF2Cl2 that I would need to vaporize in order to freeze and lower the temperature of the water for these 18 ice cubes down to -5 degrees Celsius. Now, what about sig figs here? Now, as far as sig figs go, since we're multiplying and dividing here, notice that we have 3 sig figs here, and I believe we should have about 3 sig figs here, but maybe more. We have actually more sig figs here. And so what's going to happen is that this should be limited to 3 sig figs. So 1, 2, 3. This is a 0. So then the final answer would be 1490 grams. Okay, ladies and gentlemen, that's it for this video. I hope this was helpful. If you enjoyed the video, if this helped you in any way, then please, by all means, like the video, share the video, hit that like button somewhere over here. Also, do me a favor, subscribe to my channel, help me out. When you do that, please hit the notification bell right above there. Click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.